Welcome to my YouTube channel, Physics with Einstein, and today's episode we're going to talk about the Big Bang Theory. That's right, in today's episode we're going to try to understand why and how did our universe come to an existence. So as human beings, we've always been quite rational and always try to understand why and how do things work. And one of the greatest questions we've ever asked as a civilization is how did this universe come to an existence? So theory in physics, known as the Big Bang Theory, states that our universe started 13.8 billion years ago due to a cosmic inflation in space-time. Now I agree with you that the name Big Bang just states that our universe started because of a big explosion, a big bang, and that caused everything we know now, the universe. But that isn't the case. The Big Bang Theory states that our universe started from a point of singularity that inflated accurately 13.8 billion years ago. Which also means that 13.9 or 14 billion years ago, there was no space, there was nothingness. Only 13.8 billion years ago, there was a singularity, and that singularity consisted of all the space we know. Later on, that singularity, 13.8 billion years ago, inflated, not exploded. It inflated with a rate, and that inflation caused the growing of our universe. I know that's quite fuzzy to get into our tiny brains. So let's go back to the sketchpad, where things get a lot easier. Now, in the first part of the video, I stated that our universe started due to a cosmic inflation. But what exactly is the meaning of inflation? So, have you ever recognized that whenever we say someone to blow a balloon, we regularly say inflate the balloon? Now, why is that? Inflation is a phenomena in which once matter is put inside an environment, matter creates an equilibrium between them that it expands accordingly to create an equality between both the parts. So if you see, whenever you blow a balloon, right, and you blow air into it, that is you're putting matter into the balloon, and the balloon's inner part can be called the environment. Now once you put it there, or in the field of coordinate systems, if you want to get too complicated, you will never see the balloon getting more air on this side and then getting less air on this side. The balloon will equally distribute the air which goes inside and create an equilibrium between part A and part B. That is, the balloon is inflating, which is creating a uniform expansion, and that is exactly how our universe started. If you chart out our universe in a 4-dimensional diagram, or a 3-dimensional diagram, you will never see that one side of the universe is greater than the other side. You would see the universe to be very, very equal. That is, when our universe finally emerged, it created an equilibrium, and that equilibrium is the reason why we have such a static state of the universe when it's expanding. That is, it's inflated with such precision that we never have a mismatch of where matter is. Our universe has created an absolute equilibrium. But how did all of this matter come to an existence? You see, as I said, our universe started from a point of singularity. And this can be observed at that point as the point of singularity. This dot is that singularity. But now, what is a singularity is the question that pops up in our mind. So a singularity is basically, that's it. A singularity is a one-dimensional figure that at that time consisted of all the space we know. Space in the sense, space-time, matter and everything. And this one-dimensional figure, this singularity, 13.8 billion years ago, inflated. And at the first very microsecond of this singularity, it started creating exotic particles like quarks, anti-quarks, anti-up quarks, electrons, radiations, everything with our basic consent of materialism and matter as we know. Everything we know now at its base emerged at this very first microsecond after the Big Bang. The Big Bang is nothing but the inflation of this singularity. And as soon as the inflation occurred, we finally started getting the rudimentary or the very basic pieces of matter, that is exotic particles, anti-neutrons, neutrons. And if you see at this whole figure, you can observe that our universe was rudimentarily very hotter than this, which states that at this point of singularity, one of the main reasons why it inflated, or rather exploded with a uniform precision, was because it was extremely hot and couldn't take the heat anymore. But that is just a theorem that I came up with right now. So because this was extremely hot. Our universe was extremely hot. And you will not believe, but at this point of the universe, we can actually say that energy was equal to mass, which is something no physicist can ever prove in today's life, because energy to get harnessed out of mass is something completely impossible. You've all heard of the formula E is equal to mc square, which is equal to energy is equal to mass into the speed of light square. The problem with this equation is, if you want to achieve it in reality, you have to make something travel with the speed of light twice. And because of the law of relativity, nothing can travel faster than light. So you can imagine how hot our universe was then. Still, to give you a clear picture, if you go inside the core of our sun, or if you go inside the core of the biggest neutron stars in the universe, or even quasars, you will never find the heat which was there at this point of the universe. And at this point of the universe, it was extremely hot. It was so boiling that all the energy finally started cooling down and getting transformed into matter and started creating radiations. But how do we know that all of these particles came to an existence? You see, physicists, or actually speaking, particle physicists, came up with a phenomenon known as the gas chamber. The gas chamber talks about the first 3 minutes of our universe. The first 3 minutes of our universe hold a very big stronghold, because in these first 3 minutes of our universe, we finally started getting all the matter we know now to come into existence. In these first 3 minutes, our universe started cooling down, and as the universe cooled down, by the first second, neutrons and protons started coming together and started forming the nucleus. And by the end of the third minute, we finally got the first element we know now, that is an isotope of hydrogen. So one of the things we have to remember for the next part of the video is at the very first microsecond of our universe, radiation started popping up. How does that hold strong, and how do we know that our universe, and how do we know that this occurred, and how do we know the space-time fabric, how do we know the dimensions, how can we picture all of this so accurately? And all of the credit goes to something called the cosmic microwave background radiation, which I will be talking about in the next part of the video. So mainly focus on this page, guys. In this page, these are the kind of images that are shown of how our universe is expanding. If we concentrate on this image, this is the point of singularity. This is the point of Big Bang, which happened 13.8 billion years ago, and this is what we are now. So if you see, this is nothing other than a balloon, but this is expanding outwards. You can see it expanded in such a manner that it has created an equilibrium of space-time fabric, which creates that there is enough sufficient matter to get distributed everywhere. That is the system here. And if you take a coordinate system and pull it up into this universe, we can find that matter is moreover arranged in a very systematic form. And this is the beauty of physics. You see, our universe inflated for some known or unknown reason and created a universe which has such amazing equilibrium. And this is how the scope of the universe looks now. This shows that our universe keeps expanding. And at this point, it emitted radiations, and these radiations are getting bigger, stronger, and are never stop. These radiations keep getting emitted until the year 1964, when people finally detected them. Let's go back and try to understand what I just said. Welcome back. So now we know that our universe started because of inflation, and we all know that our universe is still expanding. But how do we know that? Two scientists in the year 1965 were using very sensitive radio antennas to observe something in the empty space, but they could only get back a buzzing sound and a kind of heat signature. When they looked for more, they thought that these buzzing noises and the heat signature was caused due to the pigeons flying in the area. So they literally shot down every pigeon, but could still get back only a buzzing sound from the empty universe. They came to a conclusion that this buzzing sound or this heat signature was the reason and the explanation why our universe is still expanding. That's right. Whenever the universe expands, or when it finally started expanding, it left signatures in space which are still buzzing. And that is what we call now the cosmic microwave background radiation. This radiation is captured by many satellites, and these satellites' information state that this radiation was caused due to the expansion rather than inflation of space from that singularity? Well, again, it gets quite fuzzy in our brain. So let's go back to the sketchpad where we can make things a lot. Hey guys, welcome back to the sketchpad. So as I said at the first part of the sketchpad video, that remember that radiation started popping up from the first microsecond of our universe. But why do we have to remember that? This is the map of our universe. This is what cosmic microwave background radiation has given to us. This is nothing but a map of how radiation is right now in our universe and how it's emerging. You see, these kind of spots, or you see these colors, show the difference of heat signature. And something quite amusing is that our universe expanded with an equilibrium, which created such beauty in our universe that every 100,000 light years we find one different heat signature than the other. That is, that most of our universe has the same kind of heat. And this may seem very small to you, but this is only because it's scaled to maybe 1 centimeter is equal to a bajillion light years or something. And this is how our universe looks. You see, the radiation which started from the first minute would have started at this point, and finally it's emerged to this big of a map. And this map is nothing but heat signatures and radiations that were pulled off by those two scientists in the year 1964, and we've been capturing them from then. But let's go back and try to understand how did our universe start expanding, and who is the man who was credited for finally finding out what and how did this expansion occur. That our universe is expanded. We also know that this expansion is caused due to an inflation in space-time 13.8 billion years ago. And whenever our universe expands, it leaves a footprint behind. And that footprint is called the cosmic microwave background radiation. But the question which arises now is, how do we know that our universe is expanding? You see, in the late 19th century and the early 20th century, there were many theories which stated that our universe should remain static and there is no reason why it should expand. Then came a man, Edwin Hubble, in the year 1920, who submitted his observations, which are finally accepted to be the reason why our universe is expanding. What Mr. Hubble observed was that when he got light back from distant galaxies and measured its wavelength, it was far too long or far too big than what he expected it to be. That meant that he could observe a red shift or a shift in the wavelength, which is now termed as the cosmological redshift. This redshift or this change in wavelength stated and gave the reason why our universe is expanding. Again, it's all got fuzzy in our heads. So let's go back to the sketchpad where things always get easier. Hey guys, welcome back to the sketchpad. So before we try to understand what a cosmological redshift is, let's try to understand what a spectrum or a wavelength is. So this is how light looks. Light is a wave, and this is the photon, the rudimentary particle of light. And the difference between the two crests is known as the wavelength. Okay? And the wavelength usually defies the spectrum of light, what kind of spectrum it is. And a wavelength also defies how much energy does that kind of light have. You see, there are many types of light, if it amuses you. Like there are gamma radiations. Gamma radiation is nothing but light traveling at a very short wavelength. So this is how a gamma radiation looks. A gamma radiation has very less wavelength. We can't even see them. That is because light is traveling with such energy, because it has such a short wavelength. It travels so fast that our eye doesn't get a window to actually capture and try to understand what that radiation is. So gamma radiations are extremely fast. They have a lot of energy because they have a very short wavelength. We can create an equation which says that wavelength is inversely proportional to energy. That is, more the wavelength, less the energy. Now, visible light spectrum or visible light wavelength is something like this, right? And that is, this wavelength we're able to see with our eyes. You know, robots have infrared eyes, so they can see infrared light and visible light. So these are just kind of speculation which we have to get clear before trying to understand what the cosmological redshift is. A fun fact, if you see your TV remote, you will find a small LED there, and when you try to switch it on, you never get light out of it. That is But it isn't that the TV remote isn't giving light out. It's that your eyes aren't able to catch that type of spectrum. But if you keep a phone and then put the TV remote on and try to change channels, you can see that that LED glows. That is, our phone is able to capture that spectrum and convert it into electrical and algorithm signals and send it to the screen, and then you can finally see it in visible spectrum. But you can't. Your phone can, because your phone's lens is given the capability to try to see infrared wavelength and infrared spectrum. So that is all about it. So a wavelength is something like this. Now, if let's say Mr. Hubble was at Earth and this is a galaxy far, far away, and Earth is point A and the galaxy is point B. Mr. Hubble was observing the kind of spectrum or the wavelength he was getting back from galaxy B. And this is what he expected the wavelength to be. He expected the wavelength to be of, regular size. That is a 0.01 nanometer or something. But what he got back was something very, very big. That is, the wavelength didn't measure 0.01 nanometers. It measured 10 nanometers. Now, that may not sound such a big of difference for normal people, but for physicists, that's really shocking. Because you expect the energy of this light to be value A, where you get value X, and value X is 100 times greater than what you expect value A to be. So, when Mr. Hubble tried to think about it, he knew that if our universe is static, then, and if this much is the distance, we learned, as humans, we learned how to calculate cosmological distance by then. And he was really shocked that if I know the distance, I know the speed of light, I can also know the spectrum of light and the kind of wavelength, but why am I getting a different wavelength? He then came to a conclusion that through his observations, he can say that this universe is moving far, far, far away. And because the universe is going far away, it's expanding, the wavelength keeps changing because light takes energy to consume, it consumes energy. It is a form of matter which consumes energy to come here. Which also states and finally gives us the reason that, and a stronghold explanation which states that the wavelength can only shift. That is, the energy from that photon can only get lost where, light has to travel from point A to point B, and the distance here keeps increasing through the Euler's constant or something, which states that a rate of change of increase, which also means that the distance between these 2 points in basic term keeps increasing, and because of that, light consumes more energy of its own and spreads its wavelength more. That is, it loses energy. And because it loses energy, because it goes through so many mediums, such as stellar clouds, stellar molecules, distant galaxies, so many atmospheres, maybe because of that, the wavelength is getting longer, which states that our universe is expanding. And this is one of the craziest and one of the most basic, but the strongest and the most groundbreaking discovery in the 20th century, in the whole of cosmic science. Let's go back and see what Einstein is up to now. Hey guys, so now we know that our universe is expanding. We know about the cosmic microwave background radiation. We know why it's expanding and how did this discovery happen. But there's still many questions that can be drawn out from this video. Like, when will this expansion stop? Will it ever stop? What started this expansion? And a lot more to be discovered in the beauty of physics. Till then, like, share, subscribe to my channel, like this video, and please share it with all the physics lovers and the smart ones out there.